it's the energy required to pull off a single electron. But what if we keep pulling electrons off? You know, it's like if you pluck a daisy with all of its petals and you pluck one petal off, okay, fine. But what if you keep pulling off the petals of the daisy? What if you keep pulling off electrons? So it requires energy to pull off an electron, but if we don't stop, will it require the same amount of energy to pull off another one? Or would it be more? Or would it be less? What do you guys think? After I've pulled off one electron, pulling off the second electron, should that require the same, more, or less energy?
More.
More, because now there's more protons than electrons.
Yep.
So it's going to be more traction to the center.
Absolutely. So it's whenever you want to think about if there's attraction or repulsion, simply look to see which do you have more of. If you have more protons than electrons, then you have more attraction pulling in. If you have more electrons than protons, you have more repulsion pushing out. So in this instance, after you pull off one electron, you actually have more protons in the middle. So there's more attraction in, making it even harder to pull off another one or another one. So this is what we refer to as successive ionization energies, where you continue to pull off an electron one after another. And so it's like the equation is just kind of like that. You just keep pulling them off. So that is the majority of what we are doing on the notes today. So these are the last of them. We are finishing these up. I'm going to switch over to the iPad. So it should be the last 2 pages of that notes packet. Come on, whenever you'd like to share. No? There we go. Okay. So up at the top, successive ionization energies. Because it's ionization energy, it's still energy required to remove electrons, but it's to continue to remove. All right, so you're still moving them, but the difference is you can only take off one electron at a time and still call it ionization energy. So that's kind of the thing. But as you pull off electrons, each successive, which is another way of saying additional, each additional one becomes harder and harder to pull off because they're stuck so much more. So I want to look at this top left picture first before we look at the text at all. So we're talking about nitrogen. So how many total electrons does nitrogen have? What's its atomic number?
7.
7. All right. So nitrogen has 7 electrons. How many valence electrons does nitrogen have?
5.
It's got 5. It's in group 15. So it's got 5 valence electrons, 7 total. Its electron configuration for 7 electrons would be 1s2, 2s2, 2p3, or if we were to write its condensed version, it would be helium, 2s2, 2p3. So if I'm going to pull off an electron, where in my electron configuration is that electron coming from? The 1s, the 2s, or the 2p?
Oh, 1s.
2p.
It's going to come from the outside. So I'm always going to pull electrons off from the outside and work my way in. So my first ionization energy is going to come from removing a p electron. And that would be this guy. All right. So you can imagine that guy is pulling off a 2p electron. So if I pull off another one, I still have electrons in 2p. So if I pull off a second one, well, it's also coming from 2p. and I still have another electron in 2p. So if I pull off a third electron, it's also going to come from 2p. But once I pull off 1, 2, 3, well, then I don't have any more in 2p. So my fourth electron is going to come from where?
2s.
2s. Because now I'm in here. And there's 2 electrons there, so 4 comes from there, and 5 also comes from there. So those 5 electrons right there, the 2p and the 2s, those are my valence electrons. I've pulled off all 5 of the valence electrons. And after I pull off 5 electrons, a 6th electron, it's only got 2 electrons left. That 6th electron is coming from which energy level?
One s.
Now I'm pulling them off of 1s. So number 6 comes from 1s, and number 7 comes from 1s. These are not valence electrons. The name for those are core electrons. So you should notice there is a big difference in energy between the valence electrons and the core electrons. Huge difference. Pulling off the first, the second, the third, the fourth, and the 5th electron, yes, it does become harder and harder. It does require more and more energy each time because this is a straight line going up, right? It is more energy, but it's not that different. But as soon as I switch from taking off a valence electron to taking off a core electron, I have a large increase. That should make sense. So now let's shift over to this text box and kind of explain why. So once an electron has been removed, the remaining electrons experience, I don't know why that R is there, a greater amount of repulsion. Oh, sorry. Reduced is what I meant to do. No wonder there was an R there. Yeah, never mind me. Reduced. Reduced. All right, a reduced amount of repulsion. All right, I have less electrons, a reduced amount of repulsion, moving them slightly closer. And therefore an increased amount of attraction. As Alyssa said, because we have more protons, they're pulling them in. So we have more attraction. And if I have more attraction, more energy is required to remove it. So this here is essentially the explanation we gave like on the very before we even switched over to the notes, because I've got more protons than electrons. After I start pulling electrons off, there's more attraction and therefore more energy is needed. But that the closer an electron is to the nucleus, the more attraction there is and a higher ionization energy is what we're going to see. All right, the core electrons are closer to the nucleus. If I was actually to draw a little Bohr diagram, there's our protons. There's our 2 electrons. 1, 2, 3, 4. And there's our valence electrons, right? So these electrons have more attraction because they are closer. That should make sense that these are going to have more attraction here than the ones that are farther away. So this is going to be what gives us a large difference in ionization energy between the core and the valence electrons. So what this is going to let us do is actually look at a bunch of data and be able to figure out how many valence electrons something has simply based on the values themselves. So make sure you, let me get that out of the way. Make sure you get that top so I can squish down a little bit. So Ashira, since you just popped in, if you want to take a picture of that before I move on. All right. Okay, so normally when we talk about successive ionization energies, we don't get a diagram like the top. We get a table of values like the bottom. That's what is normally presented when we talk about successive ionization energies. So first, I just want to outline what this table is showing us, and then we can talk about it. So it says successive values of ionization energies for the element sodium through argon. So sodium through argon, those are the elements in period 3, right, in the third row down. So these would be all the period 3 elements, and they are in order, right? So we have element 11, 12, 13, 14, etc., all the way down to 18. The other thing I would say is, since we know what these elements are and what groups they're in, we know their number of valence electrons. So sodium has 1 valence electron, magnesium is 2, aluminum is 3, 4, 5, 6, 7, and 8. So each one of these, that is, right, pulling off the first electron, and then pulling off the second, and then pulling off a third, and fourth, a fifth, a sixth, a seventh, etc. Like you keep pulling electrons off. So when this over here in blue says inner shell electrons, that is another way of saying core. So the way to think about this is, yes, it requires energy to pluck off an electron. But once you have plucked off all of the valence electrons, you have finished peeling off the layer of the orange. And now you're into an inner layer. And that inner layer is like, do not touch my inner layer, my core electrons. I do not like that. And I'm going to make you pay a very, very high cost in energy to take one of my core electrons. So sodium has 1 valence electron. That's how much energy is required to remove that 1 valence electron. It's a really small number in comparison because sodium wants to lose a valence electron. So it's like, yeah, I'm going to make you give me some money, but it's going to be small. Once it loses this first valence electron, it now has 10 electrons. It's like neon. It doesn't want to do anything else. And it says, if you try and take another electron from me, I'm going to make you pay a price that is 10 times as high. And then magnesium is like, well, I don't mind losing a few electrons, so I'm going to make you pay for them, but they're not too much. But once I've lost my 2 valence electrons, well, then magnesium would also have 10 electrons, which is like a noble gas. And it's like, okay, if you want any more of my electrons, I'm going to make you pay a much higher price to take away one of my core inner electrons, because those are more valuable to me. It's kind of how you think about it. So this dividing line between the white and the blue is the difference between valence and core. And what you should notice is that it is much higher to take away the first core electron versus the last valence electron. That is a very large difference. So much so that we typically refer to it as a quote unquote large jump in ionization energies. So the very large difference between the core and valence electrons can be used to predict what group an element is in and how many valence electrons it has. Because you need to imagine that if I did not give you this information and you just looked at this chart, you could still tell that the difference between this number and this number means that this is a valence electron and this is not. and therefore that thing only has one valence electron. You can look at the numbers and see what it's talking about. So all you have to do is scan across the chart and look to see when a large jump in ionization energy occurs. That large jump will indicate moving from taking valence electrons to the first core electrons. So however many electrons you can pull off before you get to the big jump is how many valence electrons you have. So count how many electrons were removed before the large jump happened, and that is the number of valence electrons for the element. So for instance here, we've got beryllium. Beryllium has 4 total electrons, right? And it's got 2 valence electrons. We know that because it's in group 2. So it only requires 900 kilojoules to pull off the first electron. It requires almost twice as much to pull off the second one. But once I've pulled off 1 and 2, well, those are my valence electrons. So my remaining electrons, the difference between this number and this number is what we refer to as a big jump. It's almost 10 times as much. That's the kind of difference you are looking for. That kind of big jump means I have switched from having a valence to having a core. That's what it means to look through those numbers and be able to see that. So if you need to, take a picture of that, and then we'll switch to the last page. Okay. So the very last thing that we're going to cover is something called electron affinity. And electron affinity is pretty self-explanatory, based literally on the name. What does it mean to have an affinity for something?
You're naturally good at it.
Yeah, you're either naturally good at it, you naturally crave it. It's desire, right? It's like something you're good at, something you want to be able to do, So electron affinity is basically a desire for electrons. That's it. We already know who desires electrons. It's on the right-hand side of the periodic table. They desire electrons. So electron affinity technically is the energy change when 1 mole of electrons is added to some atoms. So this is making anions instead of cations. So it is the exact opposite of ionization energy, because instead of taking, I am adding. So the electron now in the equation, you'll notice the electron is now as a reactant because it's adding on to. And so everything here is opposite, meaning the things that that want to lose electrons, those are the opposite than the things that want to gain electrons. The energy values are going to be negative here. Because the creation of an anion is considered to have a release of energy. This is an exothermic process. Exo meaning out, meaning negative. So the way this works is electron affinity is the exact same, essentially, as electronegativity. So much so that most textbooks don't even mention electron affinity because they just substitute electronegativity for all of it. They are different, however, because electron affinity is taking an electron, and electronegativity is pulling bonded electrons. So they are slightly different, but essentially they measure the same thing. You are attracting and holding on. So the more attractive force you have, the more likely you're able to do that. And we already know that the elements with the most attractive forces are up here. So those are going to be the same ones that have high electronegativities. So there is a slight difference here in that, by definition, noble gases also do not have electron affinities because there's no place to put another electron in a noble gas. To make a noble gas have a new electron, you would have to have a new shell, a whole new energy shell that is an entire layer around that's even farther away, which is going to have an even smaller amount of attraction because it's even farther away. It is not favorable to force a noble gas to take on an electron. And since it's not favorable, they do not have negative values. They actually have positive values because it's so not favorable that they're like, nope, you cannot make me do it. So that's why we don't have anything for the noble gases there. The weird thing is, and one of the reasons that a lot of textbooks ignore electron affinity is because fluorine doesn't actually have the largest value, which is counterintuitive because it's got the most attraction, but it doesn't actually have the largest electron affinity. Chlorine does. And the difference here has to do with the incredibly small size of fluorine. If fluorine is going to take on another electron, because it's so small, when you shove this additional electron in, it actually creates a lot of repulsion because the electrons are too close together in that valence shell. And while it will do it, it doesn't like it as much. It would much rather just attract bonded electrons than actually take on full electrons on its own. So in nature, we don't actually see the fluoride anion existing on its own very much. It is almost exclusively in a bonded state. It prefers to get its extra electron by taking someone else's or pulling someone else's together in a bond instead of just taking it and running with it. Chlorine, however, chlorine actually exists as Cl- most of the time. And this is why hydrochloric acid is the acid we use the most, because it just basically provides chloride ions, which do all sorts of things, such as kill bacteria in pools and act as bleaching agents and do all of this other sort of stuff, because that extra electron in chlorine's got more space in its outer shell than the fluorine does. It doesn't have as much repulsion. So we don't really talk about electron affinity that much, other than the fact that it's opposite of ionization energy and essentially holds the same trend as electronegativity, and that's about it. So that's actually the end of these notes. If anybody wants to snap a picture, I'll give you a second before we switch back over and talk about the last few remaining things for me. Okay, so the last set of stuff for me is actually, I'm requesting it for Thursday to give me Friday to be able to grade it, but you only owe me two things. Video 35, which a lot of people already started doing. So that ed puzzle, and then of course the exit ticket from today. So those things. And then your only practice and application assignment is a Google Doc. It's called More Periodic Trends. It's very similar to the one that was for last week. There is no additional like concept builder or anything like that. So I'm just doing the one thing. There is extra credit available this week on Flipgrid, just like normal, but that's it. So my goal is to spend today entering all of the grades because I literally did not do any work since Friday, and I'm very proud of that. So I got to enter all your homework grades. I got to enter updated makeup work, all that sort of stuff. My priority is my chemistry kids, to get them a listing of what work they're still missing, mostly because they're missing a lot more work than you guys are. So if I don't get to sending emails to you guys this afternoon, you'll get them in the morning of any last assignments that you might be missing with direct links for those. But otherwise, that's pretty much it. So this is your last exit ticket. I know. You're so excited. Exit tickets, they're so much fun. But I did leave a space in the exit ticket since this is my only class this week. I have a couple of meetings scheduled, but otherwise I have a whole lot of free time this week where I'm just going to constantly be updating grades. So if people want to set up a one-on-one conference with me to just help you go over any last assignments or whatever, there's a space for you to indicate that on the exit ticket as people are trying to wrap stuff up. So that be it. Once you get the exit ticket, we are good to go.
Bye, Miss Baskin.
Bye.
Thank you.
Bye, Miss Baskin.
Have a good summer, everyone.